Okay, we're going to review for the test on Chapter 5, Sections 1 through 3. First question, we're asked to draw a complete graph for the following function, f of x to the fourth minus. So we get our first derivative. And we want to get our critical values so we can make a sign chart. Critical values are where the derivative is either 0 or undefined. So it's defined everywhere. So if we set it equal to 0, we can factor. We could factor out a 3x squared. So we would have 8x minus 5. And again, we're setting it equal to 0 to get our critical values. We set each factor equal to 0, so we get x equals 0. And if we set this other factor equal to 0, we'll get x equals 5/8. So if the first derivative is to change sign, it would have to be at either 0 or 5/8. Those are the values that we use to create our sign chart. So make sure you label your sign chart with f prime and label it with 0 and 5/8. Now we need just to check the value, the sign of the first derivative in each of the intervals. So we pick a number less than 0, such as -1, and we plug that into the derivative. When we plug -1 in, the first factor, 3x squared, that's positive. We don't have to worry about that. We just have to worry about this other factor. 8 times -1 minus 5, that would be negative. Positive times a negative is negative. Now we take a number between 0 and 5/8, such as 1/2, right? 4/8 would be less. So if I plug 1/2 into the first derivative, again, the 3x squared, that's positive. 8 times 1/2 would be 4, minus 5 is -1. So that second factor is negative. Positive times a negative is negative again. Now we pick a number greater than 5/8, such as 1. Plug it into our first derivative. 3x squared will be positive. 8 times 1 minus 5, that will be also positive. So the product will be positive. Now that we know when our first derivative is negative and when it's positive, we can answer some of these questions down here. Okay? We know a function is increasing when the first derivative is positive. So we can write 5/8 to infinity. We know a function is decreasing when the first derivative is negative. So we can break it up at 0 if we want, but we really don't need to. Its derivative is negative, so that would be from -infinity to 5/8. Relative max is another one we can answer. That would happen if the first derivative changed from positive to negative, but it doesn't. So we can say not applicable or none. And a min occurs whenever the first derivative changes from negative to positive. That happens when x equals 5/8. And you only have to give me the x values on that. Of course, to get the y's, you go back to the original, but that's too time-consuming for a test. Okay. Now we still have to answer questions about the concavity. So for that, we're going to need to get the second derivative and make a sign chart for the second derivative. So can I move this together? Let's see. Oops. Well, yeah, that kind of just don't move together. Let me just go back here for a second. See, even on being recorded, I make mistakes here. Okay. I'll just go down below. So to fill out the information about the second derivative, we'll get the second derivative. I'll just go back to my full view. Okay, so to get the second derivative, you take the derivative of the first derivative, and so that would give us 72x squared minus 30x. Again, we want to know when the second derivative is positive or negative, and that also can only change sign when it's either 0 or undefined, and it's always defined. So we want to see when it's 0. So to find that out, we set it equal to 0 and factor. Okay, and when we set the 72x squared minus 30x equal to 0, we see we can factor out a 6x. Mhm. And for that, it would be the other factor you'd get by dividing by what you pulled out. So it would be 12x minus 5. And then we write it as a product. We factor because a product equals 0 when any of the factors equals 0. So that would be when x equals 0. Or if you said 12x minus 5 equal to 0, that would be when x equals 5 twelfths. So that's where my second derivative sign chart, breaking it up only at 0 and 5 twelfths. Okay. So we're going to take a test value. We'll take a number like -1, and we'll plug it into the second derivative. Plug it into the factored form, makes it easier. So when you plug -1 in 6 times -1, that's negative. 12 times -1, -12 minus 15, it's -17. So we have a negative times a negative, that's positive. Now we take a number between 0 and 5 twelfths. And, if you're not sure, be conservative. Pick something like 0.1, okay? 0.1 is in there because 5 twelfths is somewhere between a third and a half. It's between 4 twelfths and 6 twelfths. So 0.1 would be nice and safe. We plug 0.1 in, or 1/10. 6 times 1/10, that's positive. 12 times 1/10 would be 1.2 minus 5, that's negative. So we have a positive times a negative, that's negative. Now we have to pick a value greater than 5 twelfths, and we'll pick 1. If we plug 1 into the second derivative, 6 times 1, that's positive. 12 times 1 minus 5, that's also positive, so the product would be positive. Now we know exactly where the second derivative is positive and when it's negative. So we can answer questions about concavity. So it's concave up whenever the second derivative is positive. So that would be from negative infinity to 0. And then also from 5 twelfths to positive infinity. It's concave down whenever the second derivative is negative. So that would be between 0 and 5 twelfths. Points of inflection occur whenever the second derivative changes sign. So that happens at x equals 0 and x equals 5 twelfths. So that's the information I'm looking for. You don't on this have to give me the y coordinates of the points of inflection and the relative extrema. So now the only other thing left to do on this first one is graph it. Now the graph is really just to check that your information is right. You can actually put it into the calculator. And if you notice on this question, you were given the window. This is your x min, that's your x max. Your y min is -0.5 and your y max is 1. So we'll set our calculators like that. So you want to enter the function into y1, and we'll set our window. Now I already have it there. So once you have the function entered, go to window and set your x min to -1 and your x max to 1.5. We're doing this so that we'll have the same view on our calculator as we are given on the graph. X scale 1, that's fine. That's what we want. Y min, -0.5. Y max is 1. Y scale 1. Good. When we press graph, wait a minute. Did I enter the wrong function? I think I entered the wrong function. Let me go back. See, I knew that was no good. Aha. Okay, this should be a 4. Okay, the window's good, though, so we can leave. Sorry, kids, it's late. I'm a little tired. So now if we press graph, we've got the right viewing window, and we have the graph. Notice it's concave up from -infinity to 0. It's concave down between 0 and 5 twelfths, right, about here, and then about here. And then it's concave up from 5 twelfths to infinity. And you can see where it's decreasing and where it's increasing. It all matches what we got. So now we just got to sketch this. Right? And let me just so it came down, concave down, and it went concave up. I probably didn't go down far enough, but I have the general shape, and that's good enough for this. All right, it does, you know, if I got an answer where where it was not increased from like 5/8 to infinity, which is, if I got something that looked different like I did at first, I would know I made some kind of mistake if my information did not match the graph. All right, but what I'm looking for in that one is that you know to get the first derivative, make the sign chart with its critical values and fill in that information. Get the second derivative, make a sign chart and fill in the other information. Moving on. View. All right. So next question, find the critical values of this function. And then identify those that are stationary points. Well, critical values are values of x for which the derivative is either 0 or undefined. All right? So critical values, we're looking where the derivative either equals 0 or where the derivative does not exist. Okay? For stationary points, they're just those values of x where the derivative is 0. Okay, so we got to get the derivative. If you take the derivative, you want to first write it, unless you want to play around with the quotient rule, you'd want to rewrite this as 4 minus x squared to the negative 1/2. So now getting the derivative, we'll use the chain rule. So we get negative 1/2. Leave the inside alone with the chain rule. If you subtract 1 from negative 1/2, you get negative 3/2. Then you multiply by the derivative of the inside, which is negative 2x. Now, in order to see when it's 0 and defined, we want to write it in fractional form. So I'm just going to rewrite that. So as a fraction, well, the negative 1/2 times the negative 2, maybe we'll cancel those first, right? This is all multiplication. If you multiply the negative 1/2 by the negative 2, that cancels out. So you're left with the x in the numerator, and the 4 minus x squared to the negative 3/2. So that would mean the 4 minus x squared to the 3/2 would be in the denominator, and in radical form, that would be the square root of 4 minus x squared cubed. So critical values are where the derivative is 0. That's when the numerator is 0. So let's identify our critical values. So to get the critical values, you want to see where the derivative is 0. Numerator would be 0 when x equals 0. Or when the derivative is undefined. That's when the denominator is 0. The denominator equals 0 when x equals plus or minus 2. So we have 3 critical values. And stationary points occur when the first derivative is 0. So for the stationary point, that's just when x equals 0. That's when the numerator is 0. All right. Next question. Using the analytical methods reviewed in class, find the absolute max and the absolute min values of the given function on the indicated closed interval. State where these values occur. When you're looking for absolute extrema over a closed interval, all you have to do is find the y-coordinates at the endpoints and at any critical values that lie between the endpoints. So let's get the critical values first. We got to get the derivative. Critical values, again, when the derivative doesn't exist, we don't have any of those, or when the derivative is 0. So to find when the derivative is 0, we'll factor. I'll factor out a 3. And so we get our critical values are x equals plus or minus 1. Now we're looking for the absolute max and the absolute min on the interval from 0 to 3. So we're going to have to find the y-coordinate at 0 and 3, and at any critical values in between 0 and 3. Well, that's just the 1. So now you just need to plug these into the original function. So if we plug 0 in, 0 cubed minus 3 times 0 plus 7, that's 7. If we plug 1 in, 1 cubed minus 3 times 1, that's negative 2, plus 7, that's 5. And we plug 3 in, we'd have 3 cubed, 27, minus 3 times 3, 9. So that'd be 18, plus 7 is 25. So absolute extrema can only occur at endpoints or at critical values. So now you compare these three numbers. So the absolute min is the least of these, which is 5, and that occurs at x equals 1. The absolute max, the greatest of these y values, is 25, and that occurs at x equals 3. All right. We have another one of these. So same idea. We just have to get the y coordinates. You don't have to make sign charts for absolute extrema. Okay? All you have to do is find the y coordinates at endpoints and critical values. So here, we're going to have to use the quotient rule to get the derivative. So let's start with that. So to get the derivative, we're going to use the quotient rule. So we have low d high less high d low all over the denominator squared. And because, to get critical values, you're going to be setting both the numerator and the denominator equal to 0. You want to clean that numerator up. If we distribute the 2x over the x minus 2, we have 2x squared minus 4x, and we still have that other minus x squared. So x minus 2 over x minus 2 squared. So the numerator, let's see, I need to give myself some more room. I'll just go down here, then I'll erase it. We have a 2x squared and a minus x squared, so we can combine that, and that would be just 1x squared. So x squared minus 4x in the numerator. X squared minus 4x, and it's over x minus 2 squared. Okay, so for your critical values, you want to find out where the derivative is 0. Well, that's when the numerator equals 0. And if you factor out an x, you would see that we'd have x equals 0 and x equals 4. Those are critical values. But we also have critical values at values of x that make the denominator 0, that make the derivative not exist. So the derivative wouldn't exist if the denominator was equal to 0, 2. So we have three critical values, 0, 4, and 2. But we're only looking for the absolute extrema between negative 2 and 1. So when we're examining y values, we only have to include them, those critical values that are between negative 2 and 1. So negative 2 and 1. Of these critical values, well, 0 is in there, 4 is not, and 2 is not. So I really only have to plug the 0 into the function of those three. Got to plug them back into the original function. Right? If you plug negative 2 into the function, negative 2 squared, that's 4. And it'd be negative 2 minus 2 over negative 4, that's negative 1. If you plug 0 in, you'd have 0 over negative 2, which is 0. And if you plug 1 in, you have 1 over negative 1. So that's negative 1. Those are the three y values we need to compare. The absolute min, the least of these, is negative 1. And it occurs at two different x values. It occurs at x equals negative 2 and x equals 1. The absolute max, the greatest of these, which is 0, which occurs at x equals 0. Right? And if you want to check your answer, you could graph the function over that closed interval. set your x min and your x max to those values and check. Okay, moving on. Let me erase all this. Okay, next problem. Find the value or values of C that satisfy the mean value theorem. So first thing you should do is the value, the slope of the secant line. So we need to find out the slope of the secant line, the average rate of change, which will be change in y's, f of 3 minus f of 0 over 3 minus 0. To get f of 3, I plug 3 into my function, so 5 times 3 squared, 5 times 9 is 45, minus 3, that's 42, plus 2 would be 44. So this would be 3, 4 minus f of 0 would be 2 over 3 minus 0. So the average rate of change, the slope of the secant, is equal to 42 over 3, which equals 14. Let's put that here for now. So the mean value theorem guarantees as long as your function is continuous over the closed interval and differentiable on the open interval, there will be a value of x, which we call c, where the derivative equals the slope of the secant. So next we're going to find the derivative, and then we'll set them equal. So the derivative is equal to 10x minus 1. So according to the mean value theorem, there has to be some number between 0 and 3 such that the derivative equals the slope of the secant. If we add 1 and divide by 10, let's see, 10x equals 15. We get x equals 1.5. Now you want to make sure that the value you get before you call it c is greater than 0 and less than 3. So you're making sure it doesn't equal 0, it's greater than 0, and it's got to be less than 3, and it is. So c equals 1.5. That's where, if you drew the tangent line to that graph, the tangent line would be parallel to the secant line. Okay, next problem, Rolle's, which is really just one particular case of the mean value theorem, when the endpoints have the same y values. Just erase this. Now, technically, for Rolle's to apply, it has to be continuous over a closed interval and differentiable over an open interval. But as far as the endpoints of the interval, they just have to have y coordinates that are equal. Well, if you're asked to find the endpoints of the interval, you could put anything you want in for y and solve, but 0 is the easiest. So to find the interval, we're going to find the roots for Rolle's. We'll find the roots of the function. So if we put 0 in, we're just looking for two x values that have the same y value, so we're picking 0. And when we factor, get x equals 7, x equals 1. So the interval that we could use for Rolle's would be the interval from -1 to 7. I'm saying the -1 first because that number is less. When you write an interval notation, whatever number is less, or to the left on the number line, you write first. So -1 to 7. So that's the interval. Now, with Rolle's, because the endpoints have the same y values, the slope of the secant is 0, so you don't have to do that part. All you have to do is get the derivative and set it equal to 0. So the derivative here equals 2x minus 6. And when I set that equal to 0, again, Rolle's, it's going to be set to 0, we get x equals 3. Again, you have to verify the number is greater than a, less than b. It's within interval, so 3 is greater than -1, less than 7. So I can call the value c. Okay, so that's where, on that interval, the tangent line to the curve would be horizontal. Its slope would be 0. So between any two zeros of a function, the derivative has to be 0 somewhere, if it's differentiable. Okay, next problem. Okay, the next problem we're asked to find, use the first derivative test for extrema to find the relative extrema. Okay. So for the first derivative test, what you're doing is you're going to get the first derivative, find the critical values, make a sign chart. If the first derivative changes sign, you have a relative extremum. If it's positive to negative, it's a max. If it changes from negative to positive, it's a min. So let's get the first derivative. We need to use the product rule. So we have first times derivative of the second. The derivative of e to the x is e to the x, plus the second, e to the x, times the derivative of the first. Now, critical values occur when the derivative either does not exist, which doesn't happen here, or equals 0. So let's set it equal to 0. And to solve this, we're going to factor, right? When you want to solve an equation equal to 0, you're going to factor, if possible. So what I notice out of these two terms, I have a common factor of e to the x. So I'm going to factor out an e to the x. And when I pull it out of the first term, I have the x squared minus 3. Pull it out of the second term, I have 2x. You can always check if you factored correctly, if when you multiply back, you get what you started with. Okay. Now, this second factor, I'm going to just rewrite. So I'm going to write this as e to the x times, I'm just going to put it in descending order, x squared plus 2x minus 3. And we're trying to see where this derivative is equal to 0. So I see that I could actually factor this second factor a little more, so I'm going to do that. We can factor that to x plus 3 times x minus 1. Okay, but now when we set each factor equal to 0, e to the x is never going to be 0. If you think of the graph y equals to the x, e to anything is always positive. That's why the graph is always above the x-axis. It's always positive. So that factor is never 0. When you set the second factor equal to 0, and when you set x minus 1 equal to 0, you get x equals 1. So those are my two critical values for this function. So I'm going to make a sign chart for my first derivative. And I'm still answering question 6. So when I make my sign chart, I mark off my sign chart at negative and 1. Now I take test values. I'll take negative 4. If I plug negative 4 into the derivative, e to the x always positive, so we don't actually have to worry about that factor. Negative 4 plus 3 would be negative. Negative 4 minus 1 is also negative, so the product would be positive. You take a value between negative 3 and 1, such as 0. E to the 0 again, that's positive. 0 plus 3 is positive. 0 minus 1 is negative, so the product would be negative. Now you take a number greater than 1, such as 2. E squared is positive. 2 plus 3 is positive. 2 minus 1 is positive, so the product is positive. Okay, so the first derivative test for extrema says if you make the first derivative sign chart and your derivative changes from positive to negative, your function has a max. So we have a relative max at x equals negative 3. If I wanted to know what the relative max was, then I have to plug negative 3 back into the original function. We have a relative min at negative 1 because that's where the derivative changes from negative to positive. Equals 1. So that's the answer for question 6. We just used the first derivative test to find the extrema. And I'll move these up here. Okay, the next one we're asked to use the first derivative test to find extrema again, and this is a piecewise function. Piecewise functions, you still, you're still going to do the same thing. You want to find out where the derivative either is 0 or doesn't exist. You got to watch those values of x when the pieces come together, like in this case 1. We want to see if the derivative exists at 1. So first we want to make sure that the function is continuous at 1. If I plug 1 into the 5 minus 2x squared, I get 3. So the limit as x of this function as x approaches 1 from the left would be 3. The y's are heading toward 3. If x is approaching 1 from the right, all right, to see what it's approaching, you plug 1 into the second branch. 1 plus 2, that's also 3. So the limit, the y-coordinates are approaching 3 from both sides, and at 1, it's also 3. So this is continuous. So far, as far as we know, the derivative exists at 3. But that's not good enough. We have to get the derivative. So we know it's continuous at 1. But when we get the derivative of each branch, we know the derivative of the first branch is negative 4x. And that's going to be the derivative when x is less than 1. Again, we don't know if the derivative exists at 1. We got to check. So don't include the 1. The derivative of the other branch is 1. Now, to see if the derivative actually exists at 1, when you plug 1 into the negative 4x, you get negative 4. What that tells you is that as you approach 1 from the left, the slope's approaching negative 4. But if x is approaching 1 from the right, we can see from this that the slope is 1. You have two different slopes. And when you have two different slopes, you're going to have a corner there. Okay? So the derivative does not exist at 1. So that's going to be a critical value. So remember, critical values occur when the derivative doesn't exist. We said not to get those, but this time we're getting that. So one value is x equals 1. We also get critical values when the derivative equals 0. Well, the derivative equals 0. If you look at the top branch, negative 4x, that'll be 0 when x is 0, and 0 is in that interval. So the derivative will be 0 when x is 0. So we are going to use these two x values to make our sign chart for the first derivative. That's what the first derivative test, that's what you need to do. You need to get the critical values. So you mark it off, 0, 1. If I take a number less than 0, such as negative 1, and I plug it into the first derivative, now I'll have to plug it into the first branch. My derivative would be negative 4 times negative 1. That's positive. Now I'm going to take a value between 0 and 1, such as a half, and plug that into the first derivative. So again, I'm plugging that into the first branch because that's less than 1. Negative 4 times 1 half, that's negative 2. That's negative. Now I take a number greater than 1, such as 2. And for that, I'm going to use the second branch. So the derivative equals 1, which is positive. Okay. So we have some sign changes. So that means we've got relative extrema. So we have, so f has a relative max at x 0 because the derivative is changing from positive to negative. And it has a relative min at x equals 1 because the derivative changes from negative to positive. Okay, now in number 8, we're asked to use the second derivative test to find the extrema. For the second derivative test, first you want to find out where you have horizontal tangents. So you get the derivative and set it equal to 0. So the derivative, 3 over 3 would be 1, so it would be x squared minus 2x minus 3. All right? You got to set that equal to 0. So again, when you want to solve an equation equal to 0, it's always good to factor. X minus 3, x plus 1. And you set each factor to 0, so you get x equals 3, x equals negative 1. So we know that our graph of our function has a horizontal tangent at both 3 and negative 1. we're going to plug each of these into the second derivative. So let's get the second derivative. The second derivative equals 2x minus 2. And we're going to plug in the 3 into our second derivative. 2 times 3 would be 6, minus 2 is 4, right? That's positive. When you get a positive value for the second derivative, that means your function is concave up. So we already knew we had a horizontal tangent at 3, okay, whatever the graph looks like. But now we know it's also concave up. So that must mean we have a relative min at x equals 3. So we have a relative at x equals 3. Now we take the other place where we had a horizontal tangent, that's negative 1, and we plug that into the second derivative. When we plug negative 1 into the second derivative, we get 2 times negative 1, which is negative 2, minus 2, which is negative 4. That's negative, right? That means your function's down there. And again, with the horizontal tangent, that tells you with this test that you have a relative max at x equals negative 1. So that's the second derivative test to find extrema. If we had 0 for answer being conclusive, then we'd have to go back to that first derivative test. Okay, number 9. I don't know. Do I have the graph? Let's see. Awesome. Okay. So here we're given a graph of the original function, and we want to determine the following. All right. So the first one says, figure out where the first derivative is 0. So that's where the slope of the tangent is 0. So anytime, so up here, right, you can see the slope of tangent would be 0, and down there. So at negative 1 and at 3. So negative 1, that's f. And when x is 3, that's I. Okay, we'll go over to B. If first derivative is positive, that's when your function is increasing. So your function's increasing over here. So from negative infinity up to negative 1, or when x is less than negative 1, that's E. Right? And it's also increasing over here when x is greater than 3, which is H. Okay, moving on to C. Estimate where the first derivative is negative. Well, that's when your function is decreasing. Your function is decreasing between negative 1 and 3. All right? If your eyes are going down as you're reading the graph left to right, your function's decreasing. So I want to look for between negative 1 and 3. That's choice A. Okay. Question D, estimate where the second derivative is 0. Well, the second derivative is 0 if you have a point of inflection. It's either 0 or undefined. So, you know, you gotta, that one's a little tougher. Let me just erase what I put over this for a second. Point of inflection, you're looking for that point where it changes from concave down to up or up to down. In this case, it's concave down, concave down, concave down, till about here. And then it looks like it starts to be concave up. So it looks like the best approximation would be at 2. Is that even there? Wait a minute. So maybe it's at 1. Yeah, maybe it's at 1. Let me just erase my little lines here. It's kind of, you know, points of inflection are a little tough. You're kind of looking to see where it switches. Yeah, you know what? I'm taking that back now. I think that is 1. Yeah, this, you know, this does look concave up over here. Okay. So, flex, cavity changes. Now we're looking for x equals 1. So that's D. Put that D in here. Okay, estimate where the second derivative is positive. Well, with that established, now we can say the second derivative is positive when the function's concave up, so that would be from 1 to infinity, or x is greater than 1. So that would be g. Estimate where the second derivative is negative. That's where your graph is concave down. So that would be from negative infinity to 1, or x is less than 1. And that would be b. So that's kind of like the very first problem, knowing function what the first and second derivatives tell you about the graph. But now we get a little more complicated. Now we're given a graph of the derivative. Now we know what the zeros are because we can just tell from the equation that the first derivative is 0 when x is 1, 2, and 4. Right, so I know that that's 1. I know that x coordinate is 2, and this one's 4. But I'm missing information that I'm going to need. Yeah, the x-intercepts are not enough. So we actually need to go to the calculator and find, I'm going to need to know the x-coordinate here at the max, right? I'm going to need to know the x-coordinate over here at the min. Now, I'm not going to make you find these on the test, but that's something you should be able to do. So we're going to just go to our calculator for a minute. Back to the calculator. Go to y equals. So we'll put in the equation of our derivative. So we have x minus 1 squared, x minus 2, and times x minus 4. Okay. So that's the derivative in factor form. I'm going to go ahead and take a look at the graph. I'm looking at the window that we're given. I'm going to match it. Let me go to my window. Looks like the x's go from -1 to 5, so I'm going to go from -1 to 5. So it's already at -1. Just change that to 5. And the y coordinates, 1, 2, 3, 4. If each little mark is 1, we might be safe. It looks like from -6 to 5 for the y's, -6 to 5. All right, let's see if this looks like what I have here. Okay. So we're going to need to know the x coordinate of the max and of the min. So to find those, we go to the calc menu. Calc menu you get by pressing second trace, and max is option 4. We'll get that one first. So when it says left bound, you just got to go a little to the left of the max. Press enter. And right bound, you go a little to the right. And you can see the calculator is showing you that it's where it's looking for the max between where those two arrows are. And then guess, you go back. So the maximum occurs, it's said to the nearest thousand, so 1.633. 34. 1.634. Okay. Now let's get the x coordinate of the min. Second calc, option 3. Left bound, which is how I'll move over a little bit. I don't want to make the calculator work too hard. Okay, that's to the left. Enter. Then right bound, you just go to the right of it. You're showing the calculator where it should look. Enter. And then go back a little, guess. So that's where it'll start guessing. And we see that that occurs at an x value of 3.366. So those values are necessary to answer this question correctly. Okay. So let me just put those on here. Okay, so we had this one here. This was 1.634. Okay, we don't really need the y coordinate since we're just giving intervals in these. And over here, the x coordinate is 3.366. Okay, now we can answer the question. Here's the first derivative. We want to know on what intervals. Well, it's decreasing when the first derivative is negative. So we look at our graph of the first derivative and see where it's below the x-axis. That's when it's negative. So we can see that's between 2 and 4. So we're looking to see where the first derivative is negative. So our answer then would be from 2 to 4. And all of these questions rely on that chart, the f prime, f double prime chart. So if I'm going too fast, pull that up. On what intervals is the graph of f concave down? Well, the graph is concave down when the second derivative is negative, but that means the first derivative is decreasing. So we got to look where what we're looking at, the first derivative, is decreasing. So it's decreasing from negative infinity to 1. So let's write that. And then again, from that, where we had that max, 1.634, all the way down to the 3.366. 1.634 till 3.366. So you were looking to see when the first derivative was decreasing. Now, part C says, where does the function of points of inflection? Well, that's when the second derivative changes sign, or the slope of the first derivative changes sign. Okay, so you're looking really for a relative max or min of the first derivative. You're looking for where its derivative, its slope changes sign. So anywhere you have a relative min or a relative max. So you're looking for where the slope of prime, that means the second derivative, the slope of f prime, second derivative changes sign. Or you could say when f prime has a relative max or min. That makes it easier. So that occurs at x equals 1. X equals 1.6. That's where it has a relative max. And x equals 3.366. Okay, part D. Where is the second derivative negative? Well, the second derivative is negative when the first derivative is decreasing. That's the same thing that we had to do for B, so we get the same answer. So, same interval. All right? So asking where a function is concave down is the same thing as asking where the second derivative is negative. We get the same answer. Infinity 1, 1.634 to 3.366. So that was a graph of the first derivative. Now in 11, we have a more typical graph derivative, right, where the values are indicated, so it won't be so hard. Okay. Man, I hope this recording works out. I'll just start again from scratch. All right, so now we're looking at a graph of the first derivative, and we want to use the indicated values to answer the following. So, you can see we're going to have this min here at -6. The max is at 1. Looks like we have a min here at 3. Well, we'll see when we get to it. Okay, so on what intervals is the function increasing? Well, function is increasing when the first derivative is positive. So you're looking to see where the graph of the first derivative is above the x-axis. So that's going to be from negative infinity to -9, between 0 and 3. Oh, and then 3 to infinity. So let's just say 0 to infinity. We can just save ink. Okay. And for intervals of increase, decrease, you do not have to include the endpoints or any of this. Okay, next one. On what intervals is the graph of f concave down? Well, f is concave down, second derivative is negative, but this is the first derivative, so we have to look to see where the first derivative is decreasing. So it's decreasing all the way from negative infinity to -6. And it's increasing then from 1 to 3. 1 to 3. where does the function of points of inflection? Function of points of inflection when the second derivative changes sign. Okay, so when the derivative of the first derivative changes sign, when the slope of the first derivative changes sign. So when the slope of f prime changes sign, or in other words, when f prime has a relative max or min. That's going to be at x equals -6. You can see its derivative would go from negative to positive. At 1, x equals 1 as a relative max. And then again at x equals 3, it has a relative min, so the slope's going from negative to positive. Does the function have any relative extrema? Well, the function has relative extrema when f prime changes sign. So it changes sign at -9. So x equals -9. And it also changes sign at 0. It does not change sign at 3, so I don't include that. So if so, identify each as a relative max or min. Well, at x equals -9, the derivative is changing from positive to negative, so we'll have a max. At x equals 0, the derivative is changing from negative to positive, so we'd have a relative min. Okay. Positive when the first derivative is increasing. So this is increasing from -6 all the way up to 1, and then from 3 to infinity. All right, one more. You can make it. Oops, whoa. I think I'll have to erase that. Oh, no, it's down here. Never mind. Oof. Now we're given a graph of the second derivative. Use the graph along with the indicated x values to answer the following. Where is a function concave up? Well, a function is concave up when the second derivative is positive. That's the second derivative, so see where it's positive. And I'll put some arrows on here. Okay, so it's positive from -infinity to a. From c to e. And that's it. Positive. Now, where does the function of points of inflection? Well, that's when the second derivative changes sign, and this is the second derivative. So it changes sign at a, so x equals a, at c, x equals c, and at e, x equals e. Do not include h because it doesn't change sign there. It just goes to 0 and then it's negative again. Okay, where is the first derivative decreasing? Well, the first derivative is decreasing when its derivative is negative, so when the second derivative is negative. This one is negative from a to c. You see how the graph is below the x-axis? And from e to h, and then h to infinity. So let's just go e to infinity. Why not? We'll just throw the whole thing in. You could break it up at h if you wanted to, but there's no reason to. Okay, so does the first derivative have any relative extrema? Well, it would have relative extrema if its derivative changed sign. So if the second derivative changes sign. And this does change sign. So at x equals a, it changes from positive to negative. So that would be a max. At x equals c, it changes from negative to positive. So that would be a min. And now I can't see. And x equals e, it changes from positive to negative. So that's another max. All right. And that's it. Oh, already? That's too bad. All right, well, enjoy this. Bye.